Hello Internet, welcome to yet another topic in network analysis and synthesis. In today's tutorial we'll study the explanation and the statement, and we'll try to understand the maximum power transfer theorem. It is one of the most important theorems of network analysis, which really makes sense in optimizing a network. So let us see the statement of maximum power transfer theorem. It says for a DC network, if we have a load connected RL to a DC network, it will receive maximum power when the load resistance is equal to the internal resistance of the source network, as seen from the load terminal. In other words, this load will fetch, or this load will receive maximum power from the network only in that case when the load resistance is kept to be equivalent to the internal resistance of the source network. And this is again understood more clearly if we draw another diagram where this block of DC source network is represented by a voltage source V0 with its internal resistance R internal, or in other words, this resistance is also known as Thevenin's equivalent resistance, and load is of course the RL. Now this RL will attract maximum power at the load if RL is kept to be equivalent to RTH. This is maximum power transfer theorem. Easier said than done. Whenever you wish to find a load that will attract maximum power in the network, you'll need to reduce that network into Thevenin's equivalent network. Then you'll need to make or tune the load network equivalent to the Thevenin's equivalent resistance. Then it'll start to fetch maximum power. And theoretically, if we see the power at the load is equivalent to I square RL, where I is V0 upon RTH plus RL square into RL, and we know that the maximum power is received when dPL upon dRL is made 0. Now what we do is we calculate dPL upon dRL from this equation, and this I will not go into the differentiation of this equation, that will make the tutorial lengthy, so I'll simply get to the final part where we get this thing. We get this thing. The value of dPL upon dRL comes out to be equivalent to 0, and we need to make it as 0 because we need to make 1 and 2 is equivalent to 0. So we get RTH is equivalent to RL because V0 cannot be 0. So you could pause the video here and look at this part of the equation carefully, and if you wish to solve this on your own, you could do so. You could refer a book or do so mathematically. But it is not of the paramount importance to know its derivation. The point here is that when RTH is kept equivalent to RL, the power transfer from a DC source network to a resistive load becomes maximum. And what is that maximum power that gets transferred to the load? This is also of interest. So this becomes the maximum power. Now here in this equation you could see that I've made the load resistance, I've substituted this load resistance as RTH. So I've gotten this thing. Again, a very important equation. I'll put a star next to it. Very important equation. And the total power which is supplied is twice of this thing, so this becomes twice of V0 square upon 4 RTH. It is V0 square upon 2 RTH. Again, important to understand because half of the power will be dissipated here and half of the power will be dissipated here. So, in other words, V0 square upon 4TH amount of power will be dissipated here, and the same amount of power will be dissipated at RL in the network. And the efficiency of this network will be P max upon P into 100, which turns out to be 50%. 50% of the power is dissipated at the internal resistance and 50% of the power is dissipated at the load. But the fact of the matter is, whenever you get a numerical where you need to find the load that will dissipate the maximum power, you'll need to first reduce that network into a Thevenin's equivalent circuit, because the Thevenin's equivalent circuit will give you the internal resistance of the DC source network. And once we find the internal resistance of the DC source network, only then we can equate our load resistance to that value to get the maximum power at the load. Now, towards the end of the lecture, I'd like to mention the maximum power transfer theorem for AC circuits. Now we know that for AC circuits it is no different to calculate the Thevenin's equivalent circuit, but what we get as an equivalent circuit is a value of VTH, which will be AC, and we get ZTH, which is Thevenin's equivalent impedance. And what load should I connect here? What should be the value of ZL so that maximum power is transferred? Again, it is pretty simple. In case of DC, it used to be RL is equal to RTH. In case of AC circuits, this load impedance should be equivalent to the conjugate of the Thevenin's equivalent internal impedance of the network. So once you find ZTH, you could simply take the conjugate of that and place that value of load as at the load to get maximum power transferred. And this is how simple this theorem is, but this is again a very useful theorem in network optimization when you want your network to function at its full potential. And I hope this quick tutorial on maximum power transfer theorem's introduction, its explanation and its statement was of some help. I'll take up numerical problems, two numerical problems, one from DC and one from AC in the next tutorial. If you like the content of this video and the other videos in the series, consider subscribing to the channel. I'll see you around. Take care. Bye.